Hello. Today we are going to start with a new subject, new topic. We have already analyzed matrices. We're going to start off with the basics of determinants today so that we can take up the more intricate and difficult parts of determinants, application of determinants and matrices in the later sessions. A determinant is similar to matrices, but unlike the matrices which is written within a bracket, the determinant is written within two vertical lines. A matrix is an array of numbers written within the bracket, but a determinant is written like a modulus, although it's not a modulus. It has nothing to do with the signs of the numbers which is written within that modulus, that vertical lines. But determinant represents a certain sum of product of numbers which are written within that bracket. For matrix A, we write A modulus as determinant A, but we don't read it as modulus of A, that is read at determinant of A. And the point to notice is that only square matrices have determinants. So only matrices of the order of 2 into 2, 3 into 3 and so on have a value which can be expressed in the terms of one single number. So square matrices having number of rows exactly similar to number of columns has any kind of determinant value. If matrix A consists of one number only, so the order of the matrix is 1, then the determinant of that matrix is said to be that number itself. So if the matrix A consists of number A, then the determinant of that matrix is known as number A only. But look at the matrix of a order 2. M into n is 2 into 2. This is a 2 into 2 matrix, 2 rows and 2 columns. We can define this matrix as A11 and A12, A21 and A22. But what does these numbers tell us? A11 represents first row and first column. A12 represents first row, second column. A21 represents second row, first column, and A22 represents second row, second column. So these numbers, they are popularly denoted as I and J. I stands for row and J stands for columns. So you can write that as Aij also. If we want to calculate the determinant of this matrix A, then it is multiplied and calculated as follows. A11 will start from the first row, first column. A11 multiplied by A22 minus A12 multiplied by A21. Diagonal multiplication and subtraction for first diagonal minus the second diagonal, because this is obviously of only 2 into 2 order only. We can take numbers to represent the matrix and calculate the value of the determinant. If the matrix is taken as 2 and 7 in the first row and 5 and 4 in the second row, we can calculate the determinant A as 2 into 4 minus 7 into 5. 2 into 4 is 8, minus 5 into 7 is 35, so 8 minus 35 is minus 27. So determinant A is minus 27. After knowing that how a 2 into 2 matrix, we calculate the determinant for that matrix, we are going to calculate the determinant for the matrix of 3 into 3. These are known as second order determinants because we have to quite remember the formulas, remember the values, so that we will be in a position to calculate them. We are going to calculate the value of a 3 into 3 order matrix by expanding along either the row or the column. Consider the following determinant. The following determinant has 9 elements in all, 3 rows and 3 columns. A11, A12, A13 in the first row, A21, 22, 23 in the second row, A31, 32 and 33 in the third row. There are 9 elements in all. The determinant for this matrix can be calculated as given follows. We take A11 and find the minor of A11. The minor of A11 is in the first row and also in the first column. So delete the first row and first column from that matrix. So we eliminate completely the first row, that is A11, 12 and 13. We completely eliminate the first column, that is A21 and 31 along with A11. So there are only 4 elements remaining which doesn't lie in the same row or same column as that of A11. So that those 4 numbers are known as the minor of A11. We take the minor to be multiplied with A11. Then we put a minus sign. We take the next number in the first row. We are expanding with the row. We take A12. We do the same thing. We eliminate the first row because A12 lies in the first row. We eliminate the first row and also the second column because A12 lies in the second column. There are 4 numbers remaining in the matrix, A21, 23 and A31 and 33. Then we put a plus sign. The first one is plus, second is minus, third is plus. This is a 3 into 3 matrix, remember. We take A13. A13 lies in the first row and the third column. So eliminate the first row and the third column. We get A21, A22, A31 and 32. That is the minor of A13. Now we have to expand it. The minor will be expanded as 822 into A33 minus 832 into 23. Then the second minor of A12 is A21 into A33 minus A31 into A23 plus A21 into A32 minus A31 into A22. By summarizing them, if you put values to this, you will be able to calculate the determinant of A. Of course, this is the formula, but we will put numbers into this, and so that we are able to calculate the values. For making it easier to calculate the value of the determinant, we should look forward to the row or column, the first row or the first column, which contains maximum number of zeros. But sometimes it is possible that we don't have any zeros at all. In that case, we can expand along with the row or column. It doesn't make any difference actually. Now we are coming to a matrix which contains elements in numbers only. So if matrix A is given as a 3 into 3 matrix, minus 2, 3 minus 1, 5 minus 1 and 4, 4 minus 8 and 2, then what should be the value of determinant A? The same thing, we take the first number A11, that is -2. We are expanding along with the row only, first row only, -2 because the number is minus but the sign is plus, so plus into minus, that's minus 2 into the minor of minus 2. We eliminate the first column, you eliminate the first row, you are getting 4 numbers, minus 1 and 2, 4 and minus 8, that is the minor of minus 2. Then minus sign, we put 3, the second number in the first row, multiplied by the minor of 3, which is by eliminating from the matrix the first row and the second column, you get 5, 2, 4 and 4. Then plus sign into minus 1, the minor of minus 1, which is 5 minus 8 minus 1 and 4. Now we have to expand minus 2 into minus 1 into 2, minus 4 into minus 8, minus 3 under the bracket 5 into 2 minus 4 into 4, plus minus 1, you can put minus 1 also, minus 1 into 5 into minus 8, minus minus 1 into 4. So 2 into minus 2 under the inside the bracket, minus 2 plus 32, because minus 4 into minus 8 is 32, minus 3 into 10 minus 16, then minus 1 into minus 40 plus 4, minus 1 into minus is plus 4, so minus 60 the first one, because it is coming to be 30 into minus 2, then minus 3 into minus 6, that is plus 18, minus 1 into 36, that is plus 36. So we get the determinant value by adding all of the 3 together to be minus 6. Here, as I have already told you, we are expanding by the first row, so you can do the expansion by using the first column also, and we will still get the same result. So it doesn't matter really whether you are expanding by the first row or expanding by the first column, you will follow the same principles. The first one is plus, the second one is minus, and the third one is again plus sign. If the number comes with a sign, then it will be multiplied with that sign. Now we have to find the number of value of determinant A, which is 124 minus 130 410. So we have to calculate the determinant A. So we expand again by the row. The first row contains 1. The first number A11 is 1. We take the minor as 30 and 01 by eliminating the first row and first column. Then we put the sign minus. The next number is 2, that is positive, so minus 2 into the minor of 2. Eliminating the first row and the second column again, we find minus 1 and 0 and 4 and 0. Then we put the sign plus. The third number is again positive 4, so we write positive 4. Then we eliminate the first row and the third column, so we get minus 1 and 3 and 4 and 1. We expand it and the value is coming to be minus 52. So the determinant of this matrix which is given to us is coming to be minus 52. So as we have already discussed, and we have done one question, that a determinant is a numerical expression of the value of a given matrix. It's a numerical expression that when you have to assign a particular number to the value of the matrix, it is called an determinant. But you should get rid of the bracket and put the vertical lines along with it. It looks like a modulus, but it is known as the determinant of that given matrix. The determinant can be 0, it can come in negative, it can come in positive. Those value of determinant depends upon the inscribed numbers within the matrix. So we don't have to worry about whether the determinant value is minus or plus or 0. Now we come to determine the properties of the determinant. As I have already told you, whether you expand the determinant by the rows or the columns, the value of determinant will not suffer because of that. So because of that property, even if you are expanding that by rows like we have done in the previous question, the answer is minus 52. If I do the same thing by expanding along with the columns, the value will still come to be minus 52. So you don't have to worry whether you have to expand along with the rows or columns. The next property, that if two rows or columns of a determinant are interchanged, if you make the column the row and make the row a column, so you just swap the rows with the columns, then the sign of determinant will change. So if sign of determinant means the value of the determinant will change, and it becomes negative if it is positive, it becomes positive if it is negative. If any two rows or columns of a determinant are identical and all corresponding elements are similar, then value of the determinant is 0 because the minors are going to be identical. The next property says that if each element of a row or column are multiplied by a constant k, then the value of the determinant will also be multiplied by k. So which means if you calculate a given determinant and the value is coming to be x, the determinant is x, and now you have to calculate the value of the determinant whose numbers are multiplied by 5, then the value of that determinant will be 5x. Every item multiplied by that number k. Next property is if sum or all elements of the row and column are expressed as sum of two elements, two terms, then determinant can be expressed as the sum of two determinants. We can derive both the determinants separately and then add it together at the end. Now we are coming to more intricate parts, minors. The minor is the determinant of a number of an element which is lying within that determinant by eliminating the row in which the number resides and the column. So if you are finding the minor of A11, so you have to eliminate the first row, you have to eliminate the first column. So the numbers you are left with are B12, B22, B23, B32 and B33. Like in the given question, if you have to find the minor of element 6, 6 lies in the second row and the third column. So you have to eliminate the second row and the third column. So which gives you 4 numbers 1, 2, 7 and 8. That is the minor of 6. This is a M23. So 1, 2, 7 and 8. 1 into 8 minus 2 into 7. That minor is minus 6. Then we come to the cofactor of the elements. The cofactor of an element small aij is denoted by capital Aij and defined as minus 1 to the power I plus j into mij, which means cofactor of A11 would be written as so if I have to find the cofactor of small a11, so cofactor will be denoted as a11, capital letter A11, which is equal to minus 1 to the power 1 plus 1, that stands for 11, 1 plus 1 multiplied by M11, the minor of A11. These are 4 numbers which are inscribed in the determinant 1, minus 2, 4 and 3. The minor of the element Aij is Mij, we are taking as Mij. So A11 is 1, so M11 is minor of A11, that is 3. M12 is minus 2, so M12 is minor of the element A12, that is 4. M21 is minor of A21, that is minus 2. The reverse elements, M22 is the minor of A22, that is 1. If you want to find out the cofactors of these elements, we have to put the formula of minus 1 to the power I plus j. So minus 1 to the A11, that is capital A11, is minus 1 to the power 1 plus 1, that is minus 1 square into 3, that is 3. A12, that is minus 1 into 4, that is minus 4. A21, 2, and A22 is 1. But these are single numbers, we are not calculating the minus as it should be. So we have taken another example which should be calculating the minus and cofactors altogether. So this is a 3 into 3 matrix. 2 minus 3 5 6 0 4 1 5 and minus 7. So we will be calculating minus and cofactors for all the elements taken together. M11 is the minor of A11, that is 0 4 5 and minus 7. Eliminate the row, eliminate the column, you get the minor. So the cofactor is minus 1 to the power 1 plus 1 into minus 20, that is 0 minus 20 to minus 20. M12 is 6 4 1 minus 7, that is minus 42 into minus 4, that is minus 46. So A12 would be minus 1 to the power 1 plus 2, the minus into minus is plus. So these are all positive values that we are imbibing into the system. After calculating all the minors, that M11 till M33, we calculate all the cofactors. We can put up the matrix of the minors that we have calculated starting from minus 20, minus 46, 30, 25, minus 4, 19, minus 19, 13, minus 12, minus 22 and 18. We can also at the same time find the cofactor matrix. Minus 20, 46, 30 is coming in the first row, 4 minus 19 and minus 13 coming in the second row, minus 12, 22 and 18 coming in the third row. So you have a minor matrix and a cofactors matrix. The values are almost similar, but the numbers has sometimes for some values, or the odd values, the signs are a little bit different, the opposite. After you calculate the cofactors, we should be able to put up the adjoint of a matrix. The adjoint of a square matrix A is defined as the transpose of the matrix of the cofactors. So to find the adjoint of the matrix A, so that is adjoint A is equal to CT, that is transpose of the cofactor matrix. You can see here, if we first find matrix A, that is denoted by the small numbers A11, A12, then we find the cofactor matrix, that is denoted by A, capital A, 11, 12 and 13 and so. We find the transpose. Transpose means converting the rows into columns and columns into rows. Then we get the adjoint. Like in the previous example, we have calculated the cofactor matrix. See from here that minus 20, 46 and 30, 4 minus 19 and minus 13, minus 12, 22 and 18. We write that here as the cofactor matrix. Then we find the adjoint A by interchanging the rows to be columns, minus 20, 46 and 30, which is the first row in the cofactor matrix. It becomes the first column in the CT. The second row, that is 4 minus 19 and minus 13, becomes the second column in the CT, that is adjoint A. The third row, minus 12, 22 and 18, becomes the third column in the adjoint A matrix. So adjoint A, you find the transpose of the cofactor matrix. So for that you have to find the minors, you have to find the cofactors, then write the cofactor matrix and take a transpose out of it. Transpose of the cofactor matrix is known as the adjoint matrix. Now we are coming to one of the most important topics in determinant theory, the inverse of the matrix. The inverse of the matrix will exist only if the matrix is a square matrix and the value of the determinant is not equal to 0, which means it's a non-singular matrix. A square matrix is said to be non-singular if determinant A is not equal to 0. Further, A is going to be invertible only if determinant A is not equal to 0, and A inverse can be calculated by the formula that A inverse a to the power minus 1, that is called as, is equal to 1 upon determinant A multiplied by adjoint A. So for calculating the inverse of the matrix, we have to find out the adjoint of the matrix which is given to us. We have already known what is an adjoint A. Adjoint A is transpose C, or transpose cofactors matrix transposed. So we have to find the determinant from the beginning, then we will find the cofactor matrix, then take a transpose, and we come to the inverse matrix. If we continue with the same example, the example we have used while calculating the matrix cofactors 2, minus 3 and 5, 6, 0, 4 and 1, 5, minus 7, then we are going to calculate the inverse for this matrix because we have already calculated the cofactors and minors. So we have to find the inverse of this matrix only. First of all, we must find A determinant. Determinant A, we are expanding again by the first row, 2 into 0, 4, 5 minus 7, minor of 2, minus 3 into the minor of minus 3, eliminating the row and the column in which that element resides, plus 5 into 6, 0, 1 and 5. Expanding that, we get the determinant of the matrix to be minus 8. How the minor is taken? If you are calculating the minor for 2, eliminate the row and column in which 2 is there, 2 is present. So you are left with only 4 numbers. That 4 numbers, put that between vertical lines. For minus 3 resides, minus 3 is present in the first row and second column. Eliminate the column. You have only 4 numbers left, 6, 4 and 1 minus 7. For 5, you eliminate the first row, eliminate the third column, you are left with 6, 0, 1 and 5. So we are determining the determinant A to be minus 8. It is not singular, it is not 0. So A inverse is, A determinant is minus 8. A determinant is not equal to 0. This means inverse of determinant A exists. We will be able to find a unique solution. We have already calculated adjoint A. In the previous slide, previous question which we have discussed. The adjoint A is clearly shown in the bottom of your slide. There is minus 24, minus 12, 46, minus 19 and 22, 30, minus 13 and 18. We put that adjoint A. The formula for inverse is A inverse is 1 upon determinant A multiplied by adjoint A. So determinant A is minus 8. So 1 upon minus 8 into adjoint A. We divide minus 8 with all the elements. We get the elements as 10 by 4, minus 1 by 2, minus 6 by 4, minus 23 by 8, minus 19 by 8. So the minus sign will be eliminated and so on. So by this process, we will be able to get the inverse. I will summarize the calculation of inverse again. To calculate the inverse, to be able to calculate the inverse of a matrix, we first calculate the determinant. Under the rules of computation, determinant of the matrix should not be equal to 0. If determinant of the matrix is exactly equal to 0, then inverse of that matrix does not exist. So we will not be able to calculate further. We are not in a position to calculate whether the inverse can be actually going to be there. So we should not waste our time. If determinant A is exactly equal to 0, we are not going to calculate A inverse because it doesn't exist. We are going to proceed only if the determinant A is not equal to 0, which means it should be non-zero. Then we find the minors, all the minors, then the cofactors. We write down the matrix of the cofactors as we have done in the previous slide. Then we take a transpose, we find CT. The transpose of the cofactor matrix is adjoint A. Then we put the formula A inverse is equal to A upon determinant A, 1 upon determinant A rather, 1 upon determinant A multiplied by adjoint A. So you can divide the value of the determinant with each item in the adjoint matrix. By simplifying, you get the A inverse. Inverse of the matrix can actually be used to find the value of unknown variables, to find the value of a system of linear equations. If a system of linear equations, suppose say 3 linear equations are given to us and we have to we have to find out exactly what are the value of the unknown variables like x, y and z, we can put the inverse formula into that. This inverse formula is known as the matrix method. We are going to discuss them forward. So this is known as the matrix method. This is one of the finest tools to calculate unconfirmed values of unknown variables. The Cramer's rule actually is not going to be used without determinants, but we can use A inverse with other methods also. So this method is very undeniably important and you must practice it. I'm going to provide you some questions with assignments. You must be willing to put those into practice, and there will be, I hope that when you practice you find difficulties which will come up, and you are going to come up with those difficulties to me, and I'll be more than happy to discuss those with you. Till then, thank you very much, and I hope that you are getting to a point where you understand at least the basic usage of determinants and matrices. In the next session, we are going to discuss applicative portions and usage of Cramer's rule. That is very important, calculation of inverse. So I hope and I will be waiting for that session to begin. Till then, thank you very much.